good evening, or good night, wherever you are. Let's get started. So today I want to talk a little bit about chain replication, the paper I signed for today from 2004. Before diving into the paper, a couple quick logistic things just I want to remind you of. One is we have a quiz on Thursday. And the instructions of the topics that are actually being covered at the quizzes are on the schedule page. We'll try to send out an announcement on Piazza with some more details about exactly how we'll do the quiz. It's going to be in grade scope, and it's basically during class hours, or 80 minutes, and more details to follow. The second thing I want to remind people of is projects. If you'd like to do a project instead of Lab 4, then you can do so, but you should submit a proposal for a project and just a couple paragraphs through the submission website, so that we can give you feedback and sort of tell you whether this project actually is appropriate for a final project in 824. If you're just planning to do Lab 4, there's absolutely nothing you have to do at all. Any questions about these sort of two logistical points? Okay, then let me move on to one other point that I wanted to bring up, which is the sort of a correction from a lecture a little while ago. We walked through the Go code for the Raft implementation of 2A and 2B that I had, and we talked a little bit about the Go defer statement. And I mentioned that you can actually have the defer statement inside of a basic block, and that is correct. And I think maybe it was Philippe who asked the question, when does that get executed? And I answered that question incorrectly. The defer statement gets executed at the point it gets returned out of the function, not if you return out of the basic block. And so I apologize if that caused any confusion. Any questions about that clarification? Okay, good. Then sort of two topics, and really the two technical topics I want to talk about today is the Zookeeper logs, which I didn't get to finish the last time, and then I'll talk about chain replication. Okay, so both for chain replication and Zookeeper, we're sort of still in the same context as before, namely we're doing replicated state machines. And just the usual diagram. We have a service that runs on some replication library like Zap or Raft. We have clients talking to the service. For example, in the case of Zookeeper, it might actually send a create call. Zookeeper internally has some state, some Z nodes that are hanging off in a forming tree. And so when an operation comes in, Zookeeper, forwards that operation basically to the Raft Zap library. It does some chatting back and forth to get a majority of the servers to accept that command. And then at some point, once it's accepted, it comes out. The service applies the operation and sends a response back to the client. And so the standard story of replicated state machine: if you start all the replicated state machines start in the same state, you apply the same operation in the same order, then you will end up in the same state. And so any of the machines can then take over if necessary. Now, one of the things that was cool about, or interesting about Zookeeper, is that read operations can be served from any service, or for any of the peers, or any of one of the servers. And this allows Zookeeper to get extremely high performance, because it can actually scale the number of read operations with the number of servers. As a flip side of that, Zookeeper actually gave up on, in that particular scenario, gave up on linearizability. Because we know from, for example, in Raft, you can't actually arbitrarily serve a read from any server. because I have not seen the latest updates yet. And so in the case of Zookeeper, that is true too. And so read operations are not, or the operation that Zookeeper defines, don't provide a linearizable interface. But nevertheless, we saw that actually it provides a slightly different sort of correctness guarantee than linearizability, and that actually correctness guarantee is useful and useful enough, to be able to write actually programs. And the particular set of programs that Zookeeper was sort of focusing on is these what they call configuration or coordination programs. And so the way to think about it is that a lot of systems that we looked at in the past, they typically have some replication story, and then they have a coordinator or a master that sort of coordinates the group. And the Zookeeper is really intended, for as a service, for that kind of master or coordinator role. And it provides a bunch of primitives, to make that doable. And we talked a little bit about atomic increment last week. And with some of the other services, and I want to sort of finish up, talking about blocks. One, because there were a lot of questions about it, and two, it actually is quite interesting. And there's sort of two different block implementations. And the first, I want to talk about the simple one, namely where, let me just write down the pseudocode, and then we can talk about it in a little bit in detail. So the pseudocode for the block was something like this, acquire in an implement loop, try to create the lock file. I'll name it LF and set ephemeral to true. And I'll talk about that in a second. Why, if the create succeeds, then, that process or that client was the first one to create that file and basically successfully gets the lock, and so it breaks out of the for loop and returns. If the client did not, be able to create the file, then it calls exists, and the call to exist is not really for see if it exists or not, because we know it doesn't exist, but basically to set a watch. And the idea is that the watch bell will go off if actually the file disappears. And if it disappears, then the client will get a notification. And so basically, what we're going to be doing here is just wait for that notification. So that's sort of the acquire operation. Then the release is very simple. The release basically does nothing else than sending a delete operation to the Zookeeper service, for the lock file. So LF in this case. And so what does that do? Well, if the delete, sent to the Zookeeper service, the Zookeeper service performs the delete operation, that will actually the file will go away. That will fire the watch. And so every client that actually is waiting, for the notification will get a notification, and then they go retry. And one of them will be successful on the retry, will get the lock file or create the lock file, and then proceed. And then the other ones, will go back into their call exists and going to wait for a notification. And the Zookeeper semantics, are good enough. The strong, the linearizability for write operations, plus the rules for when notifications go off are strong enough that basically this actually implements a faithful lock where only one client, if there are many clients at the same time trying to get the lock, only one will get it. And when the release is done or when the file has been deleted, only one in the next round will get it. And so that's sort of cool. And it's interesting that you can sort of build, sort of this foundational primitive using the primitives that Zookeeper offers. And you see here both the role of the watch, and then there's the second role for the the ephemeral is there because what happens if a client fails or crashes before it calls a release. And the semantics of ephemeral files is that the Zookeeper service will, if it decides that the client has crashed, it will do the operation. It will remove the file on behalf of the client. So even if the client fails or crashes, the Zookeeper service will decide at some point the client is done, and then will remove this file lockf, which will cause notifications to be sent to the other clients that actually are waiting for it. So it's a cool set of primitives to build powerful abstraction that can be useful in applications. One downside of this particular implementation is that it has what is called a herding effect. Namely, let's say you have 1,000 clients, they all want to grab the lock file or make the lock file or acquire the lock. One is going to succeed, and 999 are going to call exists and wait for a notification. Then when the first client deletes the file or releases the file lock, 999 are going to try to actually acquire the lock. And of course, only one is going to succeed, and then 998 are going to be sitting for a notification. But this every sort of round of this creates a huge amount of traffic, and basically bombarding the Zookeeper service, right? Because 999 are going to try to redo it again, and all but one are going to fail. And so that's a little bit of an undesirable property, this herding effect. And it's a real problem in practice, both on small scale multi-core machines, as well, of course, in a setting like this where network messages are not free. So it's interesting that actually Zookeeper provides enough primitives that you could actually do quite a bit better, that you can actually build a lock that doesn't suffer from the herding effect. So a better lock. And it's interesting, let me pull up the pseudocode for this, which is in the paper, so that we can look at it and discuss, why this lock is better. And particularly what we'll see is that this lock is better because basically there's no retry where all clients that didn't succeed getting the lock will retry to try to get it. Instead, basically all the clients are sort of form a line, and they get the lock one by one. And the way that you can program that using Zookeeper's primitives is in this particular pseudocode. And there are a couple of differences compared to the previous one. First of all, there's an additional flag passed to create, namely sequential, which basically means that these files are created. The lock file is created, but it will be created as the first one will be lock 0, then the next one will be lock 1, etc. So if we have 1,000 clients rushing to the service to actually try to acquire the lock, basically 1,000 files will be created, all numbered from 0 to 999. Then so all succeed in creating a file. The create returns actually the number that you got. So if the client 0, if the first client gets creates lock 0, then it will get a 0 back, and the second one get a 1 back, etc., etc. Then the pseudocode basically asks to get all the children in that directory under which these files are created. And so in this case, maybe that'll be 1,000 children, 1,000 Z nodes, and then you can just look at the n and see if your n, in this case 0, is the lowest Z node in C. And if that's the case, that means you got the lock. And so that makes totally sense, correct? The first client gets actually 0 back. All the other clients have a higher number because they're sequentially numbered. And so the first client will succeed in getting it. And all the other ones, what they're going to do is they're going to they're going to find the P, the number that is right in front of them. So for example, if this is client that got back, lock 10, it's going to look, for Z node 9, lock 9, and basically put a watch on that file. So this means that every client will have a watch basically on its predecessor. So he goes to see that sort of all the clients form a line, and then the client is going to wait for that notification to go off. And so that means, for example, when client 0, we got the 0 back, releases the lock, it will delete n. This will get a notification to go off for the file 1. And so the client that's actually waiting for that particular notification then will run, but it's the only one that runs, and it will succeed. And so here we see, this is sometimes these are type of locks are called ticket locks in multi-core programming, if you're familiar with them, and they have sort of the same, the same idea of sort of ticket locks is actually sort of built into this using Zookeeper primitives. And again, what is sort of interesting about it is that these primitives are powerful enough that you can actually build these kind of locks. Any questions about this? Okay, I want to make one more comment, about these locks before moving on to chain replication. And
we have a question in the chat.
Yeah. Okay. What's the question in the chat?
What is the watch for on line 4?
Good. Go back on this for line 4.
Yeah, I think that's the question.
Well, that watch. My comment with the watch is actually should go with line 5. So there's no watch on line 4, correct? Line 4 just finds P, the number that's right before your N. If that doesn't answer the question, please come back later at it. That's fine.
Actually, I have another question.
Yeah.
This is going actually, I think, back a few slides, but how does Zookeeper determine that the client has failed and thus release the ephemeral lock? Like, what if it's just like partitioned for a moment?
Yeah, no, so so that could be happen. So the client might actually, so the client has a session, correct, with the Zookeeper service. And the client needs to, actually the Zookeeper and the client basically saying heartbeats to each other. And if the Zookeeper service doesn't hear from the client for a little while, then it just decides the client is down and it closes the session. And so the client can try to send messages on the session, but the session is just closed, it's gone. And any files that were created, any ephemeral files that were created during that session are basically deleted. And so if the network reconvenes or heals, then the client will try to send messages over that session, and basically the Zookeeper service will say like, that session doesn't exist anymore. You got to retry or restart a new session.
Got it. Thank you.
Okay, good. So there's one important point about these, what I call Z locks or Zookeeper locks. And that is, they're not the same or have similar semantic as like the locks that you were using or Go locks or mutexes. And it's sort of an important point to realize, even though they're different, we'll see in a second, they're still useful, but they're not as strong as the sort of the Go locks. In particular, the case that is interesting is like when the lock holder fails. So if the lock holder fails, or basically Zookeeper decides that the lock holder has failed, correct, as we just discussed, then it is possible that we're going to see some intermediate state. And remember, like, well, the whole rule about locks is like, it's a critical section, some invariant is true, while you're going through the critical section, some of that invariant might not be true, but then at the end, you reestablish the invariant. In here, it's the case, like you acquired a lock, the client requires the lock, does some steps, and then, maybe Zookeeper decides that the client is crashed and basically revokes the lock. But the state, the system might actually be some intermediate state for which the invariant was not true, right? So it's not the case that basically these locks guarantee atomicity of a critical section. So what they do, what they're useful for, is for some other purposes. In fact, there's sort of two primary use cases. One, I think, is leader election. So basically, if we have a set of clients that need to select a leader among them, we can just, they can all try to basically create the lock file. one of them succeed, and that's basically then become the leader. And that leader, could clean up any intermediate state if possible, if necessary, or do these atomic updates using the ready trick, where basically you do a bunch of writes, to some file, but then you expose the file only at the very end, and in that way make a set of writes actually sort of more transactional work. So that's one use case for these kind of locks. The second use case is what I will call soft locks. And soft locks, the way to think about it is that, let's say we have a worker, like in the MapReduce style, and the map, and we want to basically arrange that, every worker executes a particular map task only once. And so, one way to do that would be basically take a lock out, for that particular input file, run, the computation, and then, once the mapper is done, then you release the lock file. And so this will cause only one mapper to, in the common case, to execute a particular task. And that's exactly sort of what we want. But of course, if the mapper would fail, then the lock would be released. And then, we might execute it a second time because somebody else will try to require the lock. And so in that case, for the case of MapReduce, that's perfectly fine, right? It's okay if a task gets executed twice. It happens twice. And in some ways, what it really is, it's more a performance optimization that in the usual case, you want that it actually is executed only once. But if there's a failure, it might be the case that you're executing a map job twice. And then that, and the MapReduce semantics is set up in such a way that actually that's okay. And so in those cases, these sort of locks are really useful too. Any questions about this? About this perspective on locks? That the Zookeeper locks are not exactly like the Go locks, and it's just an important thing to keep in mind. Yeah. Go ahead, Alexandra, I guess first.
Yeah, I had a question. You said that one of the differences is that in Zlocks, if the server holding the lock dies, then the lock can be revoked. But does that still happen if you don't pass the? Because there's that flag called ephemeral.
Yeah, ephemeral. Yeah, that only happens with the ephemeral file.
Right. So can we just like emulate the Go logs by not passing ephemeral?
Okay, good. What would happen then? So you create basically a persistent file. The client dies.
You just have deadlock.
And so the lock will keep on existing, and nobody will release it. And we have a deadlock. Because the one person that could release it is dead. Or crashed. And in fact, this is like why the ephemeral part is there.
Is it actually the only person who could release it? Because anyone can delete that file, right? Could you have a background like?
But that would break. But that would break. Maybe the other client is still running and also still thinks it holds the lock.
Sure.
You guys are getting sort of at this. Basically, this is the consensus problem all over again, right? And so this is sort of a clean way to get most of it, but not all of it, if you will. And I think if you want to make things atomic across a number of a set of writes atomic, you basically use this trick of you use this trick of basically the ready trick, where you do a bunch of writes and then you expose them at the same time.
Could you explain the soft locks again?
Okay, soft locks means that basically an operation can happen twice. And so in the common case, if there's no crashes, it will happen once, because the client will take a lockout, will do the operation, release. But if the client failed halfway through, for example, then the lock would be automatically released by Zookeeper, and then maybe a second client will execute the same map task.
So in the case of leader election, what's the intermediate state that could get exposed here? I mean, it seems that first, yeah.
I guess in a pure leader election, there would be no intermediate state, but typically the leader will create a configuration file, correct? As we saw in Zookeeper, where, using the ready trick.
I see. And so you just write the whole file and then convert it atomically, you just rename it.
Yep.
Okay, thank you.
Sorry, could you explain what the ready trick is exactly?
I was hoping not to, because I think we talked about it last time.
Sorry.
Right. So maybe you can hold that question, and I'm happy to do it at the end of the lecture again. Because otherwise I have little time to actually talk about chain replication. Any other last minute questions? Okay, let me set the stage for chain replication a little bit, and then we'll also come back to Zookeeper in some sense. And basically, it turns out there's sort of two common approaches to build replication state machines. And we really haven't called out these two approaches. We've seen them, but I haven't really talked explicitly about them. And I want to do this time explicitly. So, because there's some interesting observations to be made. Approaches to building replicated state machines. And the first one is the one we basically have seen in the labs, which is you run all operations through Raft or Zookeeper or Raft or Paxos, whatever consensus, distributed consensus algorithm that you're using. And so this is sort of like the key value store, right? In lab 3, where you do put and get operations, you run all the put and get operations through Raft, and the services basically update the key value store state as they operations are coming in on the apply channel, and and basically we have our replicated state machine. So this is sort of like how lab 3 works. It turns out that style, where basically Raft is used to also run all the operations, is actually not that common. We'll see some other designs later in the semester that do that too, like Spanner does it. But it's not actually completely the standard approach, or the more common approach actually is to have a configuration server like Zookeeper. Service. And the configuration service itself internally, might use Paxos, Raft, or Zap, or whatever. And really, the configuration service is really plays the role of the coordinator or the master, like the GFS master. And in addition to basically having configuration service that is actually implemented using one of these Raft Paxos algorithms, you actually run a primary backup replication. And so think about GFS, or that we saw early in the semester, has that sort of structure, right? In the GFS, there was a master, and that basically determined, which set of servers hold a particular chunk. And so basically determined the replica group for a chunk. And then the replica chunk group basically executed a primary backup replication. One of the chunks was the primary, and the other ones were the backups, and they basically had a protocol that they used for primary backup replication. And you can think about VMVT in a similar style, where the configuration server is basically a test and set server, which basically recorded who was actually the primary, and then the primary and the backup have a protocol to basically send channel operation down the channel, and so that the primary and the backup is sort of roughly in sync and implement a replicated state machine. And this approach tends to be sort of the more common approach. Although the approach number 1 also happens. One way to think about this is that if the Raft state, like for example, our key value server in lab 3 would be gigantic, have a huge amount of disk state, terabytes of a key value server, would Raft be a very good match for that kind of application? Or what is the risk or the potential problem?
We flush the lock very often, so maybe that could be problematic.
That could be problematic. Yeah, like what's the size of the checkpoint if our key value server is really big?
It's linear in the size of the key value store.
Yeah, so the checkpoint is going to also be gigantic, right? So if any time the checkpoint has to be sent, it's going to be a big checkpoint. And sort of like Raft is not really sort of set up, and so the primary is going to communicate, the new primary is going to communicate these snapshots that you did in lab 2D, to the backups, and they're going to be big. And so you often want to maybe a little bit more clever plan to sort of synchronize, resynchronize new servers. And and one reason that basically often these things are split into two different pieces, where there's the configuration servers that basically small in terms of state, and then a primary backup plan that actually may replicate a huge amount of data. And so this is why one reason you see sort of both approaches. Does that make sense? I'll come back to that at the end of the lecture again, but it's important to keep this in mind.
So what approach or what benefits does one give over two?
You don't have to have two of them, right? In one, you basically have Raft, you run the operations for root, and then it does the configuration for you too. And so everything is in a single component. And here in number two, we have two components. We have a configuration service that includes Raft, and we have a primary backup scheme. So maybe this will become more clear as I talk about chain replication.
Yeah, I had a really quick question. So like essentially for two, I guess would the advantage be that you have like is consensus reached through the leader and the leader never fails, right? Like
yeah, so the advantage of two is that, as we'll see in a second, in chain replication, is there's sort of a separate process that takes care of the configuration part, and you just don't have to worry about it in terms of your primary backup replication scheme. And that just decides, like in GFS, that's sort of like the master. It just decides, okay, well, here are the set of servers that form this particular replica group. And the primary backup protocol doesn't have to think about this.
Thanks.
And so, and this is a good introduction to chain replication, because the chain replication is exactly sort of a primary backup replication scheme for approach two. And that is to say that chain replication assumes there is a configuration service. I think they call it the master process in the paper. Then chain replication itself has a couple cool properties. One, read operations, or as they call them, query operations, involve only one server, namely the tail, as we see in a second. Another nice property about chain replication, it has a very simple recovery plan. And we're going to talk about all of these in more detail in a second. And presumably something that you start to have, you appreciate, given the fact how complicated it can be in Raft, and it provides actually strong properties, namely linearizability for the put and the get operations. And finally, just a lot of people ask this, there's actually a reasonable influential design, and is used by quite a number of systems. So it's actually used in practice. So I'm going to talk about each of these components in a little bit more detail, and then we'll come back to this sort of approach one versus approach two. So in terms of an overview, oops, what happened here? In terms of an overview, here's sort of the lay of the land. There is a master process or a configuration service. And that basically keeps track, of which servers, belong, to a particular chain. So S1, S2, S3, basically have a record of what the chain is, who the head is, and who the tail is. And so that's the configuration server. So in here, we do actually have our servers, S1, S2, S3, And one of them is the head, typically the one with the smaller number, and one is the tail. And so if we have a client, the client may talk to the configuration server, learn, who actually is part of the chain, and then it sends a write request to the head. So this is the protocol in chain replication. The write request always goes to the head, and what the head does, the head basically pushes. The head actually applies the operation on its state. Maybe it has a disk, associated with it, where whatever stores key value server on it, and then it sends the update, the result of the operation down the chain in FIFO order and reliably. So S1 will send the update to S2. S2 has its own disk, apply the operation or the state change to its state. Once it actually has applied it, it will forward it to the last node in the chain. In this case, because there are only 3 nodes in this particular chain, you could have chains that are longer, if you want more availability. And when the last node gets the message or the state change, it applies it to its state, and then it is in charge actually of sending an acknowledgement back to the client. So it's the tail who sends the acknowledgement back. And so one way to think about this is that when the tail, or in this case S3, actually applies the state change, that's sort of the commit point. And the reason that this is the commit point is because subsequent reads always come from the tail. So if anybody or any other client, does a read operation, they always go to the tail, and the tail basically responds immediately back to them. So read operations go to the tail. So here was client 1, here's client 2. Client 2 does a read operation, it goes to the tail responds, and that's it. And so there's a couple things that I want to sort of point out. One of the interesting points out is that the read operations just involve one server. Right? And if you remember from lab 3, or as you in progress, if you started to do lab 3, read operations actually involve, in our implementation, read operations go through the raft, log, and all that kind of stuff. The paper discusses an optimization. But the read operation always goes to the leader, and the leader first has to contact the majority of the servers before it can execute the operation locally. So what you see here is that the read operations actually go to a complete, so to a different server from write operations. So the read and write workload is actually spread at least over 2 servers. Furthermore, the read operation involves only one server. There's never, it doesn't have to talk to any other server, it can just respond immediately. And we'll see a little bit later why this is actually important, or why this is actually, what further optimizations this allows. And so the commit point is really, at the point that the write actually happens at the tail end, because at that point, the write operation is visible to readers, and not before any later point. And this also, provides this linearizability. So it's pretty easy to see that in the case of no crashes, this scheme guarantees linearizability because the writes are all applied in some total order at the head. And when the tail receives, that update, it's the commit point. It will respond, to the client and send the request back. If that same client immediately does a read operation, it will go to the tail and it will observe the last change. Certainly within a single client, basically all operations are totally ordered. It's pretty easy to see that if client 2 starts a read operation after client 1 operation has finished, and when is it finished? When the tail has responded. So any read operation that starts after a write operation will observe the last, or the result of the most recent write. And so it's pretty easy to sort of get an intuition here that this is going to provide us with linearizability. Okay. So what I'd like to do now is actually take a quick breakout room section, and where I would like you to discuss the question that was posed in lecture. What could go wrong, or like, would it break linearizability if instead of having the tail respond to the client, have the head respond to the client immediately after it has received the a write request. And maybe that's a good topic sort of to debate a little bit. And if you want to go in any other direction to talk about chain replication, of course, you're welcome. But maybe that's something to start with. So let's take a 5-minute breakout room, and then we'll do this. And I think, let me see, Jose, are you going to do it?
Yeah. Okay,
Do I have to make you something, or?
I don't think it's necessary.
I think Zoom changed, so it should be possible now to. Yep, that's great.
Yep. Okay.
Hey, Jose, are we coming back?
Yeah, whenever you.
I'm ready.
Okay, and then I think I can close the phones. Yeah.
I think everybody back. Okay, good. So, just quickly to summarize, why, that would break linearizability. Yeah, so the protocol change that was sort of contemplated was to, both, keep propagating to S1 and S2 and S3. But, as soon as S1 actually is done with its propagation, it send a response back to the client. And clearly that would break linearizability because let's say this client 1 did the write, got the acknowledgement back, from S1. S1, of course, has, the write also in progress to S2 and S3. But maybe before, S2 actually contacts S3, the client actually sends a read operation, to S3. And of course, now it will return the value from before the write was done. So the client doesn't even observe its own writes. And so that would clearly break linearizability. So it's very important that, as I said earlier, that the tail actually sends the acknowledgement back, to the client, because really once the tail has processed the writer operation, that is actually really what the commit point is. Any questions about that? Okay, now, so this was sort of normal operation. And I want to talk a little bit about crashes. Since it's 824 distributed systems, so all the actions is when the failures happen. And one of the things that is cool about chain replication is, the number of failure scenarios is actually quite limited. And so so basically there are 3 cases, namely the head fails, one of the intermediate servers fails, or the tail fails. And so let's look at each of those cases. So here's the case. We have a head, it's S1. Let's just say that it applied U1, U2, and U3, so 3 updates. Talks to S2. Maybe S2 has done U2 and U1, and we have S3, which is the tail, and it only has done U1 so far. And so the client was talking to S1. And we now want to think about what happens, what needs to happen if one of these crashes. And so let's start with the case that the head crashes. And so the head crashes. What needs to be done? This is an easy case. This is a hard case.
Easier.
Yeah, it's an easy case. Why, Philippe?
You can just cut off the head. The head, and make S2 the head now.
Yeah, right. We could just promote, so what's going to happen, correct, is that the configuration server discovers that S1 is gone, or decides that S1 is gone, and then basically can promote S2 to be the head in the subsequent operations, and clients in the future then talk to this guy. And why is this correct? So what operation have we lost?
We lost U3.
Yeah, and is that a problem?
That's valid to lose operations. Or
yeah,
to fail.
so, Yeah, it's fair game to lose U3, correct? But U3 has not been committed because only operations at the tail are committed. And so it's just as if the operation never happened. The client could not even have observed, that actually that this U2 or U3 actually has happened, or U3 has happened. Okay, so it's perfectly fine to do this. Why is it important that the configuration server is actually involved here? Could like ST2 decide on its own to become the head? Let's say S2 couldn't talk to S1 anymore and decides like, whatever, I want to become head. Would that be valid?
Wouldn't that like maybe create a split?
Yeah, that would create that would create a split brain, correct? Because it might, S2 might then just be partitioned from S1, and so now both are heads, and maybe both start processing commands, and that would be, violate our, basically the sort of this whole property of having a total order. We cannot
also, does S2 even know that S1 is a head? Because it just receives.
It probably got it from the configuration information in the previous time, right? Like when configuration server decides on the new configuration, they can tell all the servers and whatever and the clients that actually care. Here's the new configuration.
Wait, does this only happen when like S1 to S2 connection is separate, or wait, what? So what causes the split brain again?
The split brain would happen if S2 on its own decided that S1 has failed and became the head. And so we're not allowed to have that happen. And the way actually the will work out in practice is that there is a configuration server that actually decides what is actually the current configuration. And so if it decides that S1 is dead, then it can inform S2 and S3 saying like, hey, you guys are now the new chain and S2 is the head. And when that change happens, so in this case, basically S1 is dropped, nothing else has to happen. Because S2, the only update that we lost is the one that actually was not committed anyway. So there's nothing to be repaired further. So making this, going from this setting from 3 replicas with the dropping the head is basically a pretty straightforward operation. Okay.
Professor, I have a question. So there's an assumption here, right? That like the commands that like leave S1 like will arrive in order
Yes.
in S2. Is that a reasonable assumption for like?
Well, I think with the way they so they basically say we need a reliable FIFO between S1 and S2, right? And from S2 to S3. And I think the way they basically implement that is probably using TCP connection.
Okay. Thanks.
Okay, so let's look at the second case. So we here have, we get S1, S2, S3, and of course there could be more, servers in the chain, but like, 3 is enough for us to consider all the cases. And so now what we want to do, take the case where a middle one crashes. So this one crashes, and so the configuration server at some point decides, S2 is crashed, informs S1 and S3, basically they form the new chain. And we're wondering about like what else needs to happen. Okay, we saw in the first case, if the head drops, then nothing really has to be done other than updating the chain. Now we're updating the chain, and the question is, does anything needs to happen?
The S1 needs to send to S3 the request that it sent to S2 but didn't make it to S3.
Yes, exactly. Right. So we have U1, U2, U3. This guy had seen U1 and U2. This guy had seen U1, and the U2 that's actually in progress. And I got lost by S2. Basically, S1 has to bring S3 up to date and basically forward at U2 and U3. Okay, so there's actually a little bit of work involved. Well, let's consider the final case, the tail. So here we go again. We have 3 cases. S1, or the 3 servers, S2, the third one, S3, and let's see. So the tail crashes, and so at some point in time, the configuration server notices, decides that the new chain is going to be S1 and S2, tells S1 and N2 that they're part of the new chain, and what else needs to happen? Well, let's write down we know these guys have seen U1, U2, and U3. This guy has seen U1 and U2. So who becomes the new tail in this scenario?
S2.
Yeah, S2 becomes the new tail. And anything else that needs to happen?
I guess the client needs to be informed that S2 is the new
tail. Yeah, so the client might learn this from the configuration server, correct? And so, yeah, but nothing else has to happen, right? Because all the committed, no committed operations are lost. And S3 are still in, needs to still be actually propagated to S2, and that will be just happening. Okay, so dropping the tail is also reasonable straightforward. So dropping the tail and the head is reasonable straightforward. Dropping the middle one is a little bit more complicated, but not much more complicated. And the key thing, though, I want to sort of emphasize here is how does this compare to figure 7 and 8 in the RAF paper? Maybe to, yeah, go ahead.
I just have a question. So when S2 becomes the new field, don't we need to commit the entries that are in S2 but haven't been sent to S3? So don't we need to send acknowledgements back to the client saying that these new operations have been automatically committed?
Sorry, I didn't hear you. You were pretty, it was a pretty noisy connection there.
Yes, so like I was just saying that S2 becomes the new tail. Don't we have to send acknowledgements back to the client that there are some entries that have been automatically committed?
Yeah, that might be the case that what will happen is the client is probably going to retry, correct? And we have to have a separate duplication scheme like in Lab 3 anyway. And so there's a couple different ways about how to do it. The paper's actually not particularly clear on which one it will take.
Okay, I see. Thank you.
Yeah. Like in that case, didn't the paper just say like, it might, like, even if it doesn't respond, it could or could not like have succeeded, right? Like,
yeah. So. Okay, so back to my actually original question, which is like, how does this contrast this picture on my drawn picture here on this whiteboard? How does that contrast to figure 7 and 8?
Simpler.
Yeah. I think that's the key point I wanted to get across, correct? Because there's not that many cases to consider here. Basically, 3 cases, which is like slightly, quite a bit simpler than in the case of the RAF paper, where there are many configurations to consider, and the scenarios are quite complicated. Now, part of that is because it's a chain, right? Things are pushed down in a very sort of straightforward manner down the replication chain. And part of that is, of course, the configuration part is sort of outsourced to the configuration manager. But for the primary backup part of the recovery plan, that's reasonable straightforward. There are only 3 configurations to consider. Now, one more sort of point I want to make, which is like, how to add a replica, because any system, that you're going to run for real, at some point, you got to add a new one in. Because otherwise, you're going to lose. You start with 3, then you have 2, then you have 1, and then you have 0, and then you're unavailable. So, you have to add new replicas. So let's consider the case. So here's S1. It is the head. And let's say we were in a scenario where we have S1 and S2, which is the tail, and basically we want to bring up S3. And it turns out, as the paper described, that it was most convenient to actually do this at the tail end of it. And so basically make the new server the new tail. And so the way that would proceed is like, so the client is here, it's talking to S2, because that's actually the current tail. S3 comes up. And basically what the first thing it does is actually it copies all the state from S2 to S3. And so this may take hours, right? Or tens of minutes, or maybe indeed multiple hours if like we're copying gigabytes of data or terabytes of data from S2 to S3. But while that's happening, S2 and S3 can just serve requests. Of course, it does have to remember which ones came in after S3 started copying. So keep a list of like all the updates that are sort of have happened, but have not been propagated to S3 yet. At some point, S3 is done, with all the copying, and basically tells S2, okay, man, I'm ready, to become the tail. I got all the state. S2 said, and so sends an email, basically sends a message to S2 saying like, okay, I want to be the tail. S2 responds, says like, yeah, that's okay, but once you applied all the updates. And so basically S2 sends the updates in response to this, I want to become the tail request, in response to that to S3. S3 applies the updates and then becomes the tail. And clients that were talking to S2, and S2 can tell the client, from now on, I'm not the tail anymore, you should talk to S3. And so they can swap, their direction. And so that's the way to add a replica into a chain.
So question on this, don't you run into this like infinite loop problem where S2 sends updates to S3, and when S3 is like updating, it's also serving more requests, and so as more updates that needs to send and goes back and forth?
No. Like once S2 has sent the updates that S3 has not seen yet, to S3, then from then on, it's normal chain replication. Whenever S2 gets a request, an update from S1, it forwards it to S3.
Right, but S3 can't become the tail until it is successfully processed all of the updates, right?
Oh yeah, so once it sets up the TCP channel, basically S2 can just say like, from once you have processed these guys, you can become the tail because you have seen everything.
I mean,
and everything else, can be pipelined after that, right, in the same TCP channel.
It could become the tail right after, like even before it processes the updates, right? As long as it doesn't serve requests.
As long as it doesn't serve requests, exactly right. It just has to process all the updates that S2 has received and S3 not. Once it's updated those, then it become the tail and start processing requests.
I see. So it blocks like requests for a moment while it processes the new updates. Got it.
Yeah, exactly. Okay. Okay, so now I want to come back, to basically questions lots of people ask, how this contrasts to sort of, how are the CR properties, chain replication properties? How does it compare? What are the good properties, and mostly, with respect or in comparison to Raft. And of course, I got to say, of course, like the chain replication just implements the primary backup scheme and not, the configuration service. And so we'll come back to that a little bit more in detail. But there are a couple of things that we can note if we just compare sort of the way the Raft protocol works with the chain replication protocol. And first of all, we can observe, positive aspect of chain replication is that the client RPCs are split between the head and the tail. And so the load of actually serving any client operation can be split actually between two of them. They don't have to all run through the leader as in Raft. Furthermore, the head sends an update once. So unlike in Raft, where the head or the leader basically sends updates, the log entries to every peer, in this particular scheme, actually it's only happened, the head only sends one basically RPC. And so there's sort of fewer messages involved. Reads or query operations involve only the tail. All right, in the Raft, even if you implement the read-only optimization, the read-only optimization avoids having the read operation go through the log and being appended to all the logs of the peers, but it still requires that the leader actually contacts the majority of the peers to decide whether it actually the operation can be served. And so another positive aspect of this plan is simple crash recovery, as we talked about. But a major downside, compared to sort of the Raft scheme, is that one failure requires reconfiguration. And the reason the reconfiguration is required is because like a write actually has to go through the whole chain. And so, and then write cannot be acknowledged until that every server in the chain actually has processed it. And that is actually slightly different, correct, in Raft, as you well know, because as soon as basically a majority of the peers actually have accepted the particular write operation and appended to their logs, the system can just proceed. And so there's actually no interruption at all if like one server fails, for example, and if the remaining servers still form a majority. While in chain replication, if one server would fail, then some reconfiguration actually has to happen, which means there's going to be a short period of probably downtime. Right? Does that make sense? Now, I want to make one more point, sort of in contrast, to sort of the Raft replication scheme, is that because the read operations involve only one server, there's a cool extension, if you will, that actually gets really high read performance. And so the basic idea is as follows. The basic idea is basically to split, the split objects, or they call it volumes in the paper, split the objects across multiple chains. So instead of having one chain, as I would have done in the previous boards, we're going to have multiple chains. And so, for example, we might have a CH1 in chain 1, S1 is the head, S2 is the middle guy, and S3 is the tail. In chain 2, we're going to rotate things around. S2 is the head, S1 is S3 is the middle guy. Whoops, S3 is the middle guy, and S1 is the tail. And in chain 3, we're going to arrange it basically S3 is the head guy, S2 is the S1 is the middle guy, and S2 is the tail. And basically what we're going to do is we're going to split objects across these multiple chains. So the configuration server basically has a map, saying like, shard 1, objects in shard 1 go to chain 1, objects in shard 2 go to chain 2, objects in shard 3 go to chain 3. And what is the cool part about it is that we have now multiple tails. And S1, S3 is a tail for some chain, S1 is a tail for some chain, and S2 is a tail for some chain. And basically read operations for these different chains can now be completely executed in parallel. So if the read operations sort of hit all the different shards, sort of uniformly spread, then basically, our read throughput is going to increase, linearly with the number of tails that we have. And in this case, we have 3 tails, so we get 3 times the read performance. So we get basically sort of same as we get a little bit of the same properties that Zookeeper had, where the read performance can be excellent. It can scale with the number of servers, but we also get not only that, we get the scale part, but we maintain the linearizability. In this scheme, we don't have to actually give up on linearizability. So we get sort of the 2 nice properties, namely good read performance, in fact, scaling with the number of servers, at least for reads of 2 different chains, and we got actually and we maintain linearizability. Any questions about this?
Sorry, in this case, the client, when they are deciding which chain to read from, would they be able to do it, like to decide themselves, or do they need to contact the configuration server to decide?
Yeah, so that's a great question. So typically, and the paper actually doesn't really say it's explicit about it. They talk about maybe talking through some proxy, to the servers. What you will do in lab 4 is basically you will download the configurations. The configuration will include the shard assignment, and you will download that from the configuration server.
Do you need to be careful about how you order the servers in each of the chains to prevent like a particular chain from being oversaturated, or a particular link between like 2 servers?
This scheme doesn't really take that into account. You can imagine like the configuration planner, the configuration manager have a sophisticated model of actually how the network is laid out, and can be very careful about how the chains are done. Maybe even shard more shards to one chain and fewer shards to another chain. All that stuff is in principle possible, right? Because the configuration manager can just compute anything it likes and basically says, here's the assignment.
Thank you.
I can even rebalance if it wants to. So the question, could you explain again how linearizability is kept under this extension? Well, nothing has really changed. We're still doing primary backup using a chain. And so we basically carry over the linearizability from the single chain, and that's it.
This might be like speculative, but how would this compare to, or I guess maybe it's equivalent of just like having groups of servers for each like link instead of reusing the same ones, or not for each link, but for each step in the chain. So like S1 is like 3 servers, S2 is 3 servers, instead of reusing the same one and entering from different points.
Yeah, well, what would be the advantage of that scheme that you imagine?
I mean, just for scalability, while also maintaining linearizability.
Well, the reason that this scheme is attractive is that because the head and the tail might have quite a bit of load, but the middle guy doesn't. And by having sort of this arrangement, we spread the load across all servers.
I see. Okay.
Okay, good. So maybe I want to summarize here. And sort of talk a little bit about, so we saw this approach 1, which we do in lab 3, which is, we run all the operations through Raft, and all the replication, the configuration and the replication is all built using Raft, and nothing else is involved. And then sort of this approach 2, which is the topic of this particular paper, where there's a configuration server, perhaps built using Raft or Paxos or anyone, and a primary backup replication scheme, and primary backup using chain replication. And you can see, hopefully, this lecture makes a little clear that there's some attractive properties to approach 2, in the sense that you can get scalable read performance on the primary backups. Of course, not in the configuration server, because it runs Raft like you do in approach 1. But you get at least maybe a scalable read performance for actually your operations on the replicas or on the primary backup scheme, like the put and get operations. And the other thing that is nice about this is that sort of if you have your data is very, very large, you can have more specialized synchronization or schemes to basically copy the state from one machine to another machine. And the chain replication or any sort of primary backup scheme that's sort of separated from the configuration server allows you to do that easily. And so it's quite common that in practice people follow approach 2, although it is also not impossible to actually use approach 1 for your replicated state machine, including servicing operations like put and get operations. And in fact, as we see in lab 3, we do it. We will see later a paper in the semester called Spanner that actually uses Paxos to actually also do the operations. Any further questions here? If not, then I wish you all good luck on the midterm on Thursday, and I'll see you in person, well, virtually in person, next week. And if you have any questions, please feel free to hang around, and I'll try to do my best to answer them.
I have a question.
Yep.
I have a question about something that you mentioned about Raft. So you mentioned that all of the reads have to go through the majority of servers, but I'm not quite sure I understand why, because the leader has all of the committed entries, right?
Yeah, there's two schemes. If the leader, so either you run into a situation where all reads and writes are served by the leader, right? Or there's a possibility to serve in principle a read operation from another peer, but then you have to contact either first the majority of the servers to make absolute sure that you have the last operation.
Got it. So that requirement is if we want to spread all of the reads across every peer.
Yeah, then we have to be more sophisticated. And we cannot do it on our own because that would definitely break the interoperability.
Right, but if everything goes through the leader, we don't have to do that.
Then you're golden, correct? Except you have to do this trick where you have sort of an empty agreement at the beginning of every new term, just to make sure that you actually are up to date.
Okay, thank you.
Could you quickly go over again when you're adding a new server at the tail? So just to make sure I understand, so essentially it starts this process for like copying all the data from S2 to S3.
Yep.
And then if it receives requests for any of that data while that is still happening, then S3 is going to like ask S2 for anything that it still has directly, and it's going to get it and then respond.
Yep.
And then it keeps doing that until it gets data that S2 no longer has, and then it just goes live essentially.
Yeah, or you could do slightly differently. You could actually have S3 could basically tell S2, S3 can become the leader or the sort of the tail, and basically don't process any common operations from the client yet until it actually has received the remaining operations from S2.
Oh, so in that case, S2 is still the tail.
Yeah,
until S3 gets everything.
Yeah.
Okay, thank you.
There's basically the paper describes one particular way of doing it. There's a couple ways of doing it.
But if you do that, then like how long do you wait to get everything? I think I also had the same confusion as someone else.
Oh, you know in what order the switch is happening, correct? Like, so for example, like S3, so S2 is, let's say, maybe has update operations through 100. You start the copy operation. It's like with the snapshots in the Raft. You start the copy operation. So when the copy operation is done, S3 is up to date until 100, correct? Then, maybe S2 already has done 10 more operations. So it has 101, 102, and 103. Right, and basically S3 can contact S2 and say, so give me your remaining operations, and S2 says like, well, my remaining operations are 101 through 110, and as a side effect, S3 also tells S2 like, stop being the tail, and S2 responds with those operations. S3 applies those operations 101 through 110. And then tells client, and in the meantime, it is tail, but it doesn't process any commands from clients yet, or read operations from clients yet, until it actually has processed 101 through 110.
Okay, I see. I see. Okay, makes sense.
Wait, so
I also had a question.
Yeah.
Oh, sorry.
No, go ahead. Yeah.
Oh, okay. My question was a little similar to the extension that you talked about. I thought about could you do a tree instead of a chain? So
I think there's there are other data structures possible. Like, for example, a number of people in email proposed that you could have S1. Then you could have like S2, 3, 4, 5, all the intermediate ones. S1 talks to them in parallel to all the intermediate ones, and then the intermediate ones talk all to the tail. Is that what you mean with a tree?
I meant more if there would be like a number of leaves that would be at all roughly the same height, so like a balanced tree, and then the leaves will have like a chain going through them. And I think that like linearizability can be broken here if you like, if
Okay.
you think harder about it, but it would have the nice property that you wouldn't like the propagation delay would be like logarithmic instead of
Definitely.
linear as here, and you could read from all the leaves, but
Yeah, okay, so reading from all the leaves is dangerous, correct? Because they might have, one client might have talked to another leaf earlier, and the leaves might not be in sync. So that sounds dangerous to me, but maybe your scheme is a little bit more sophisticated than I'm thinking. The depth of the tree or the depth of the chain is really governed by the mean time to routine failure, correct? If the mean time, if you typically run with 3 servers or 3 to 5 servers because that's good enough for your high availability, then because you can recover from 4 servers before the whole thing is down, then that really governs the depth of the chain. And yeah, that will introduce some latency.
okay, that makes sense. Yeah, thank you.
Change will generally be short.
Right. Okay, that makes sense. Thanks.
You're welcome.
Is this the only case where the entire chain would go down if all of the servers in the chain went down?
Yep.
Thank you.
I also was curious how you maintain the strong consistency when S1, S2, and S3 can all do the read in this slide.
You get strong consistency per per shard or per object that's assigned to the chain, correct? So if you read, you write one object, you write object 1, you read object 1. All those operations are going to go through the same chain, and so you get strong consistency for that particular object.
Oh, got it. But it may not be the case that across all the objects we have strong consistency.
No, I don't. I will. Let me hesitate on that. Let me hesitate. I think that requires maybe more machinery.
Wait, what does that mean? Across all the objects, getting strong consistency?
I think you read write object 1, you read or write object 2, and then some client reads your object 1. Are you going to basically, if you have a client that reads both objects, are you guaranteed to see total order and linearizability?
Is that like serializability?
The serializability is slightly different. Maybe let's not talk about serializability. We'll come back. We'll get that later in a couple of weeks. I'm hesitant to actually make a commitment right now. I need to think a little bit about it.
Okay, that's totally fair.
Wait, so the question is you have consistency or linearizability for a single client reading and writing, but not for multiple objects.
You have even multiple clients talking to this, doing operations on the same object have strong linearizability, correct, in this scheme. The question is, do you have linearizability across objects too?
But why is that important? I don't see where that would be important. Because you're gonna you can't group operations, right? So a write and a write are two, right?
I mean, you read object 1, you write object 1, you read object 1, then you read object 2, you write object 2, and the question is, in linearizability, those operations need to be total ordered, and they need to preserve this property of real time. And since you have different chain, that might actually not happen. But I don't want to commit to no statement about it at all across chains. Within the chain, it's absolutely guaranteed linearizability, even if you have different objects.
There's something I don't understand in the paper, which is the update propagation invariant.
Yep.
Where in this order of the chain.
Yep.
The commits are prefix of each successor's commits.
Yep.
Is that guaranteed after like a full pass has gone through the chain?
No, it's always true, correct? Like, if you go back to this picture here, I think to make a basically very simple observation, which is, well, let's see if I can find a good picture. I probably scribbled over everything, so it's going to be maybe not as clean. Basically, what they're saying, like if you look at this figure, correct, that S3 always has a prefix of S2, and S2 always has a prefix of S1. And that's the only thing that basically that invariant says.
Oh, so I and J, so the one out, the successor has the prefix of the predecessor.
Yeah, and this is slightly confusing. I just realized that later after somebody else asked this question. In the definition, the I's and J's are used in two different ways. Well, not really in different ways. One is a definition, and one is actually the invariant. You're going to be a little bit careful. The roles of the I's and J's in the
I thought it was the other way
invariant.
around.
Yeah, exactly.
How's that possible? Okay.
Exactly.
Thank you.
You're welcome.
I have a, oops.
Yeah.
Sorry, go ahead.
I was just gonna ask, what happens when you have like a network partition instead of a crash? So if you go to like the crash slide, what happens to the chain if there's a network partition? So maybe something like S2 is actually still alive, but there's a partition between the configuration manager and S2 or something. And so now both S1 and S2 are pointing to S3.
No. Yeah. Okay. Yeah. Okay. There's going to be some. Presumably, what I think the paper doesn't talk about this, but I presume that all configurations are numbered, like a view number, and S3 will not accept any commands from S2 if the view numbers don't match.
Okay, got it. Thank you.
So related to that, one thing I couldn't figure out is even with like configuration numbers or something, how do you make sure that when you get rid of the tail in like the third scenario that you've drawn, that when you get rid of the tail, that all the clients that might issue a read are aware that this old server is no longer the tail?
The clients, I think the way you would do it is that the configuration server, when the client downloads the configuration from the configuration manager, they also include the view number. And every operation includes the view number, and S3 will see, hey, that's an old view number. Don't talk to me.
I guess when then does the client talk to the configuration server to get a new view number? Because I guess I'm worried about the scenario where there's a client that has an old view number.
So, for example, the S2 could just retry, say like retry, and the client then could go back to the configuration server and reread the state.
I guess what I'm worried about is like S3 has been network partitioned away from the coordinator, and so the coordinator like gets rid of S3 from the tail and increases the version number. But some client out there doesn't find out that the version number is increased and still thinks S3 is the tail, talks to S3, does a read. Meanwhile, people are doing writes to S1, S2, and they haven't heard it, or they haven't seen that basically.
Yeah, this is probably the reason why in the paper it goes through the proxy.
I see. Okay.
I have a question, kind of going back to that like unanswered question about kind of like cross-object linearizability. I guess like, is that a whole another can of worms that we haven't really talked about, which is like if you want to do, I don't know what the right term is, but like transactions that like cross multiple pieces of state. Like if you're trying to implement an operation where it's like you're setting A to 1 and B to 2, and you should only see those together or not at all, like atomicity of that. Have we talked about that in any of the things we've seen before?
No, and we'll talk about it in a couple of weeks.
Okay.
It's going to be a big topic. I basically have to do transactions.
Okay, that's good to know. Thanks.
Do you mind going back to like the third slide?
Yep.
I think it was the third slide. Maybe not. Fourth slide. Oh, fifth slide. Sorry. So I was a little bit confused when you mentioned like if lockholder failed in intermediate state stuff. What exactly on this slide applies to Z-locks and what applies to the Go locks again?
These are almost all statements about Z-locks.
So is the first statement that if the lock holder fails, then the intermediate state is not cleaned up or is cleaned up?
No, the intermediate state is visible. But then, for example, if you have a leader election, you could clean up that intermediate state. That was just like the point.
Oh, so with Go locks, is that also not the case? Like if there's a machine that's holding a Go lock that's doing stuff and then it all of a sudden dies, isn't still the intermediate state visible?
Okay, I think what I'm talking about is Go locks, is something that is a statement about multiple threads running on the same machine, correct? And so if the Go lock disappears because the machine crashes, all the threads on that machine crash too.
Right, but when you say that the intermediate state is visible to other people, that's still true for Go locks though, right?
If they've written persistent state to disk or into some shared file system, but like, no, the machine is gone, the disk is gone, everything's gone.
Oh, got it. Okay, so it's saying that the persistence, like the intermediate state is persistent.
The Zookeeper intermediate state might be visible, right? Like the guy might have created some more files, and those are visible now.
Okay, I see. Thank you.
So just to follow up on that, so it's the implication that if a Go routine ever dies while holding the lock, the entire Go program must have died too.
Yep.
And you can never have like a Go routine die holding a lock and like have other parts of the program continue living.
Yep.
Okay.
If the Go routine crashes, the application crashes.